Hello, I'm Thebaud and I'm going to present you unsupervised labeling of stolen handwritten digit embeddings with density matching. Publication for the workshop Security in Machine Learning and Applications, October 2020. First, a bit of context. Biometric authentication systems are widely used. You certainly have examples of voice, face image analysis or fingerprint analysis in your smartphones. And here we are going to talk about handwriting analysis, specifically on digits. But generally, biometric authentication systems use biometric data, and this is personal data and does need to be protected. In a general biometric system, biometric data is used to is passed through a neural network extractor to compute highly dimensional representation that's supposed to contain the identity of the users and are often called embeddings, templates, or X vectors, depending on the kind of biometry. Oftenly, biometric data is the more protected part because it's raw personal data. So, for example, in Europe, we have the GDPR, and this data is a priority data to be protected. But here we're going to focus more on the neural network extractor and the embeddings part. What can we retrieve from them? Recently, there have been multiple publications about template reconstruction attacks that use neural network extractor and templates to recover the associated biometric data. For example, the template reconstruction attack of Mai et al. On deep face templates. They use the black box access to neural network extractor and deep face templates to regenerate the associated face images. Those kind of attacks shows that not only the biometric data but also the other part of a generic biometric system needs to be protected. Here we are going specifically to talk about unwritten digits system, biometric system. So in our system we use unwritten digits as a sequence of 2D points, not images. Pass them through LSTM RNN embedding extractor to compute embeddings that are supposed to contain the identity as well as the digit values of those drawings. For the simplification of our hypothesis here, in this publication, the stem will only be trained to detect digits. So embeddings are in general authentication systems are stored or exchanged for authentication purposes and other purposes. So because of that storing and exchanging, they are sensible to attacks. The starting point of this paper is the question: what if the attacker got access to embeddings, and only to embeddings? What could he do with it? What could we do if we had them? So let's detail a bit our threat model. Let's say an unlabeled set of embeddings of dimension 64, extracted from a handwritten digit authentication system, is stored in a database. No encryption, no template protection scheme. Let's say this database is stolen. What could we do with it? There are 10 digits. It's a digit authentication system, so we suppose the embeddings can be clustered in 10 digit value related clusters. And if we can cluster them, we could guess the value of those clusters of embeddings. And this is the goal of our attack. Here we want to find the digit values of the clusters of embeddings. To help us a bit on this attack, we added two additional hypotheses. The first one is a weak hypothesis about our knowledge of the original extractor. We suppose the attacker knows the architecture of the extractor. It's a weaker hypothesis than knowing that having a black box access, because we don't have access either to the weights or to the initialization, only to the architecture of the extractor. And also we can see in the literature that most of the paper about unwritten digit authentication systems use LSTM for encoders. So we have this first hypothesis, and our second is that given the nature of the data, an attacker could easily craft or find a set of unwritten digit sequences. So with our two hypotheses, we are going to see how can we attack this system. So let's see it. We have an unlabeled embedding set that we'll call U, the U set for unlabeled. We know this set has been extracted by an LSTM RNN from unwritten digit sequences, but we don't have access either to the network nor to the database. But for our two extra hypotheses, we can suppose we know the architecture of the network. We have another set of sequences from a disjoint set of users to not add any complicated hypothesis. And so we use this disjoint set of sequences to train our classifier, our extractor, and extract a labeled set of embedding. Because we have the knowledge of the previous sequences, we can know the digit value labels of those embeddings. So we have our unlabeled set U and our labeled set L. Here is a visualization of both of those sets. In the upper part, the unlabeled embeddings are represented, projected into a two-dimensional space using principal component analysis, and the different colors of those embeddings are for every numbers. For example, here the red embeddings are the 3, and the yellow one are the 8. In the lower part, it's exactly the same thing, but with the L embeddings. So we can already see there are similarity in the structures. Both sets of embedding naturally form digit value related clusters, so the clustering shouldn't be a problem. If we go further, once they are clustered, we can guess statistical information about that distribution, like their variances along different axes, because they are originally in a highly dimensional space. Here they are just projected for your visualization. And what could we do? What could we guess from there? In this attack, we are not supposed. Firstly, we're not supposed to know the labels of the U embedding. So once clustered, we have 10 cluster of U with an unlabeled cluster of U, and 10 classes of L where we know the label associated to each of the L classes. Here we want to find the transfer matrix W to do the flow, the transfer between both spaces. And if we can transfer the U embedding into the L space, the cluster that will land on the cluster of 2, for example, will be a cluster of 2 embeddings. So to label the unlabeled cluster of U, we want to find that transfer matrix. Finding the transfer matrix between two sets of embedding is an exercise that is proper to, that is usually found in unsupervised translation publications. So we looked in that way, and we found one example, the Zhu et al. Publication, density matching for bilingual word embedding. So what did they do? They trained a rotation matrix between both space of embedding and both space of word, two space of word embeddings from different languages. They trained the matrix to maximize the log likelihood of one set projected to the other. Then they compared the projection of one set into the other using their matrix with the Gaussian mixture model trained on the other set, and the opposite to have an inversible symmetric transfer function. And they also added weak losses, weak constraints on the fact that it should be a rotation, and they achieved pretty good results. Our problem here is that this method didn't work on our problem, so we wonder why. Why? It's because they used a special initialization proper to translation. They suppose that they had the knowledge of the few thousand more frequent words of each language, and suppose a correspondence between them, so that could have used this first correspondence to initialize correctly their matrix and then fine-tune it. Because we don't have access to any of the labels of the U embeddings, we can't use that initialization. So we had to find another way to do it. So to do it, we use the degraded rotation matrix equivalent. We used for any given permutation matrix, permutation that established the link between the cluster of U and the classes of L. We computed using Procrust and the centers of the cluster of U and the cluster of L a rotation matrix. This rotation matrix isn't a 64 by 64 matrix, it's a 10 by 10 matrix, because with using Procrust with 10 correspondence, 10 pivot points, we couldn't have a higher dimension than 10 dimensions for rotation, so we reduce both the embeddings, the clusters, to 10-dimensional space using a principal component analysis. So we can, using a given permutation matrix, we can generate a rotation matrix associated using Procrust. It's not the perfect rotation matrix associated to this permutation because it only uses the center of the clusters, but still we have a way to find, for a given permutation, the associated rotation. This rotation, we can score it using a log likelihood score detailed in the paper, but it's basically the sum of the log likelihood score in using the matrix in one way, projecting the U embedding into the L space, and in the other way, projecting the L embedding into the U space with the inverse rotation. So we use that log likelihood score that compares projected embedding with Gaussian mixture models to score a rotation matrix, so to score a permutation, a given permutation. Because we only have limited options for permutation, if we try to link 10 clusters to 10 classes, then there is only 10 factorial possibilities. We evaluated all of them, so it uses a certain amount of time, but we can generate every permutation matrix, every rotation associated, and compute every score. And here is the box plot of the different scores by the number of errors of every permutation. For example, the genuine one is at 0 error because the 0 cluster is associated to the 0 classes of L, the 9 clusters of U is associated to the 9 classes of L. If we look at the permutation with 3 errors, there will just be 3 exchanges between the associations. And by looking at that graph, we can see that our genuine permutation, the permutation we want to use, without knowing it, is one of the best permutation. One of the best, add one of the best scores. So we to gain a bit of time, use the genetic algorithm. By experimentation, we found out that the genuine permutation, the best permutation, was always in the 21st permutation, the 21st ranked permutation according to our log likelihood score. So we use a genetic algorithm to select the 20 best permutation in that 10 factorial permutation space. And after getting that 20 best permutation, 20 candidates to be the best permutation, we only had to apply to them our fine-tuning described earlier with our log likelihood loss and 2-week loss over the rotation part on the determinant and the inversions. So we take our 20 candidate permutations, compute their associated degraded rotation using Procrust. We fine-tune our 20 candidate rotations to get 20 fine-tuned rotations that are supposed to be in the local optimum, and we re-rank them. Once re-ranked, the absolute best rotation is actually became actually the best permutation. Is associated to what we consider to be the best permutation. And after experiments, we did that whole algorithm using different data splits, 100 different data splits to get 100 different experiments. And over those different experiments, the genuine permutation always ranked first, or the best rotation we wanted to get always ranked first over the other over 100 experiments. So to resume, we have the genuine permutation that is known. So we have a method that can label every time correctly the clusters of U. And we have, with our fine-tuning method, a reliable transfer function between both space and embedding, but still in reduced dimension, because we had to reduce the dimension using PCR because we only had 10 clusters, so 10 dimension maximum. So to conclude, we can resume our contribution in two steps. First, we inferred the label of the cluster of 110 digit embeddings every time we did it. And secondly, we computed the transfer function between a label space and comparison space in limited dimension, and used a rather original way to do it using unsupervised translation techniques. For our future works, we have a few questions that are still in our scope of research. Firstly, we only used classifiers trained on detecting the digit values of sequences. What if you used classifiers trained on the identity also? Could we also find a transfer function in a higher dimension, not in a PCR reduced dimension? Could we execute a template reconstruction attack with finally only the embeddings, the storing a labeled set of embeddings, and the architecture of a network? Could this method work with an unknown architecture? Are different networks extractor similar enough to produce a similar embedding even with different architectures? And would that method work with different biometries? So those are the main points we want to explore in the future, and we are already working on the three first. Thank you for your attention, and feel free to ask any question or remark on the Slack or the direct presentation. Thank you.